Welcome everyone. My name is Danny Torres. I am the co-team captain for our team from Appalachian State University, and this is our solution for the University of Central Florida Solar Plus Storage District use case. So our team structure is composed of 4 undergraduate students and a faculty advisor from the Department of Sustainable Technology and the Built Environment at Appalachian State University. Some of us had a running knowledge of solar PV systems and battery storage, as well as project development and construction. So with that being said, we allowed for all of our team members to choose which part of the project interested them the most and to work on that. And each part of the project was developed in conjunction with one another. So we all kind of worked side by side on this project as it came to be.
So our first goal with this project was to maximize the PV production within the given constraints from the university and the utility company, while also maximizing the benefits, the economic and financial benefits for the university. Additionally, we have some recommendations for the integration of educational aspects to the system, since UCF is an educational institution and part of their master plan involves the development of a sustainable campus culture. And finally, we strive to make our system reasonable for all parties involved in the project.
So to start off, some initial system design constraints that we faced while constructing our project. There was limited on and off campus areas for solar system, mostly on campus area. We were given 13 building rooftops, as well as three parking lots on campus to design our solar installations. And so our next major system design constraint we ran into is for our off-campus ground mount system. It was not allowed to exceed the daytime minimum load of the university, so that required us to size those systems down, as we will explain in the later slides. And so given these constraints, our final design system was only able to offset about 3% of the university's total consumption. And finally, outside of system design constraints, another constraint we were faced with is the state of Florida does not allow for normal purchase power agreements. So we had to model our project after a sales leaseback financial model.
So after the careful analysis of all of the restraints that we were given on the use case study, the aggregate system size of all of the systems we designed is about 110 megawatts. And will produce about 16 gigawatt hours annually. And with that, through a battery model developed by both our team and Dr. Reichel, our faculty advisor, we found that a 10 megawatt hour size battery would be the most effective if UCF chose to go that direction. And moving on to our on-campus system design, we created a nameplate size of about 5.5 megawatts. This is spanning across 12 rooftop systems and 3 carport systems. And we used about 14,000 Jinko Solar 400 watt panels. And we chose these panels as they were manufactured in Florida, which will help cut down on transportation cost of materials, as well as the embodied carbon emissions of the systems collectively. And we used both a ballasted and a flush mounted racking systems sourced from local manufacturers and used depending on the slope of the individual roof that we used. If we move on to the next slide here, you'll see pictures of all of the systems we designed. We really tried to fit as much power as we could into these systems while eliminating shading loss. And over here on the bottom right, you'll see that we created 3 carport systems to work in conjunction with our 12 rooftop systems. We also explored a ground mount system of about 2.7 megawatts, which was our calculated daytime minimum load. And we used about 7,000 modules over just under 7 acres of land on the site provided by UCF. And we utilized the existing service roads to allow for ease of access for maintenance crews working on site. They're using the same Jinko Solar 400 watt panels, as well as a Solar Flex ground screw type racking to allow for to minimize cost and to allow for a quick installation time. The battery system will also be located on this site, as it's very close to the utility corridor to the south of this system. Well, we also looked into a floating array on the pond available to us near the baseball and football stadiums. We were able to reasonably fit about 1900 kilowatts on this bit of lake. And to supplement the 1900 kilowatts to get it up to that daytime minimum load, we also created a second array on the Neptune Drive site in the shape of UCF's logo, so they could use it for promotional material to help them promote green energy on campus and inspire more people to get into renewable energy. The floating system is going to use Fasten Solar's floating mounting system. This was because we weren't able to locate a manufacturer in Florida, but because floating PV is such a up and coming bit of the renewable energy sector, this was the most readily available mounting system available for our systems.
So now we'd like to go back and fill in some details about the model we used to arrive at the results shown on a previous slide. So once we realized that our system would only offset about 3% of the campus's load, we knew that if we were to prioritize offsetting that load, there would not be enough energy left to charge a battery system fully from the PV. So for this reason, we opted to use our personal power flow model so we could switch to prioritizing storage, specifically charging when the energy rates are low and discharging when rates are high. And we came out with an optimal system size of about 10 megawatt hours. We made an assumption about how much energy we would reasonably be able to harness on a given day. And our plan for the batteries became charging from the grid overnight up to about 70%, and then topping them off with solar energy once the sun rises. And they would then discharge during on-peak hours only, so that we can provide favorable economics to the university by reducing their total on-peak energy charges and only charging from the grid when the rate is 1 cent per kilowatt hour. But because our proposed PV will offset so little of the campus's load, we've concluded that we would not recommend adding an energy storage system at this time. At this system size and with the given constraints, even when we prioritize charging, the system would not make enough of a difference to rationalize adding it, and the university would save more money by just investing in solar. That said, if the university would still like to pursue a battery system, our recommendation would be the Tesla Power Pack. It is one of the more expensive options on the market, but it's highly customizable, so we can have it do exactly what we need it to. It has a high round trip efficiency, outdoor rated enclosure, and comes with an integrated inverter system, so we could cut down on additional costs by just wiring it into the campus when they arrive. And as far as location, as mentioned previously, we would opt to put our batteries in one location alongside our ground mounted PV, since the trees there would have to be cleared anyway, and it would provide the most energy.
So looking at the university's electricity cost per year, breaking down their different demand charges, customer charges, as well as their very competitive energy charges that they are charged under Duke Energy. Their on-peak energy charge from Duke Energy is 6 cents a kilowatt hour, while their off-peak charge is 1 cent a kilowatt hour. And we found this to be a very competitive rate that is charged to the university by Duke Energy. And we came to the conclusion that that the university has a energy bill before inflation around $11.7 million a year. And with that being said, as a developer, we would see a favorable cost of electricity per kilowatt hour that we could offer to the university as 12 cents a kilowatt hour. And over 20 years, this could save the university around $2 million. And we got to this result by assuming that the cost of grid purchases will steadily increase at a rate higher than the escalation rate of the cost of electricity from the solar system and the developer. And we also assume that there would also be possible carbon taxes and other limiting factors that would cause the price of grid electricity purchases to increase over the 20 years. So that number isn't exact, it's just around $2 million that the university could save with this offered cost of electricity at 12 cents a kilowatt hour. And then the next party in the sales leaseback, and this model is the developer, and the developer, and as listed in the table below, would see more money up front if they were to look into developing a PV and battery system. But over the 20 years of the sales leaseback, the developer would net more of a profit with the PV standalone system. And as you can see in the graph below, around year 14 is when the system will pay itself back. And then finally, the last party involved in the sales leaseback model, the investor. The investor can see a $12.3 million net profit after the 20 years from the standalone PV system, which is, as you can see, it's a lot less than the PV and battery system, but we believe since this is still a great profit and the PV standalone system is attractive for both the university and the developer, that the investor should still be attracted to investing in the PV standalone system. So for our development plan, first we would need to receive roofing, solar, and electrical permits from the city of Orlando per their Orlando solar submittal codes and requirements, which should only take the first few weeks of the project. We modeled our project over a 6-month construction timeline, as we'll explain more in the next slide. And we aim to start the project in the months of January and February because our months of construction will be months 4 and 5 around that time to start. So being our construction will start in months 4 and 5. If we start months January or February, this means that we would construct the project while most students and faculty are away from the campus in order to avoid major disruptions to campus operations. And finally, we try to design all of the parts of our project in compliance with the university master plan of 2020 to 2030, to where they wanted to see more sustainability throughout their campus, as well as clean energy installments. So as you can see, as mentioned in the slide previously, our construction timeline is a total of 6 months, with construction beginning in months 4 and 5.
So here we have a number of recommendations for the academic integration of this system into campus to help the university get excited about solar and about sustainability. So first off, we would like to work with the computer science department to create a website for the systems that would allow interested parties to view real-time data. We'd encourage the university to implement aspects of sustainability into their education to promote a more sustainable campus culture. We'd also have interactive kiosks set up around UCF's memory mall so that passersby can find more information about the solar systems. Additionally, we would propose a possible research project for the biology department relating to the effects of floating PV on the life in and around the pond, since little research has been done there so far. And finally, we do have the UCF-shaped supplemental PV system mentioned previously that would stimulate pride among students and others associated with the campus. So to summarize our progress on this project, we were able to provide a solution that works within the given constraints and that follows the university's master plan for their campus. We attempted to design a viable battery system, but after tweaking our power flow model and analyzing our PV system with and without energy storage, we ultimately concluded that a battery system would not be viable at this time. And our final proposition benefits all those involved, and we're confident in its design.
So some final recommendations we would have for the university were first to open up more of their campus for solar installations and opportunities. We were only given about 13 buildings, and we used that to the best of our ability. But if the university would like to offset more of their energy and reduce more of their carbon emissions, we would recommend that they would open up more of their campus to allow for those. And then our other recommendation is just to scratch that and invest in more land further away from their campus, far enough away so that possibly they wouldn't have to register the land as a qualifying facility through Duke Energy. And so that way they can offset as much of the campus's energy as they would like to, without having to worry about exceeding the daytime minimum load. And this would also fall right under the campus's master plan and would make UCF a leader in clean energy across the country with other universities and reduce their carbon emissions greatly. So yeah, we would like to thank everybody for coming out to our presentation today and seeing what we have done the past semester in our research. And we would like to thank the competition organizers for this incredible learning experience. If anybody has any questions about our project or about what we do here at Appalachian State with our sustainable technology program, feel free to reach out and contact any one of us at our emails below.